and welcome everyone. This is the pilot class for science and technology, and we are starting with the topic of semiconductors. As you can see, we will be discussing everything in and around semiconductor and why it is very important topic for UPSC preparation, especially UPSC prelims. So, let us begin. Why chips matter? Alright, from sand to silicon. As you all know, most of you already know that from sand we get the prime element, prime compound basically to make the silicon chips. So, we will go through this journey and we will get to know that what is there in and around and why is semiconductors a very burning issue not only in science and technology, but it is affecting geopolitics and national security concerns as well. So, let us begin. Here we can see there is this snippet of NDTV website, and this is quite recent news of 26th June. Apple's biggest price hike yet. Biggest price hike yet. Why Macs, which is MacBooks, iPads, many of you already I believe use iPad in your daily activity, suddenly cost up to 1 lakh more, 1 lakh rupees more. Alright, so most of you already know this news. There is also scarcity of Apple products in market, online and offline both. So, this current affair, this single news has a direct implication from the semiconductor industry, or we can say semiconductor ecosystem. Moving ahead, why did Apple products suddenly have a sharp price increase? What exactly is a semiconductor? Why has it become so strategically important? And finally, why is India trying to build a semiconductor ecosystem? As I said, that semiconductor is not an industry in itself, but it is an entire ecosystem. So, these are some questions that we will be moving along and we will be discussing, and we will get to know why of all of these questions, the answer of all of these questions. Alright, so moving ahead, we will start with the basic, you can say, dictionary meaning of semiconductor, and we will go back to our classes, childhood classrooms, and this is nothing non-familiar for you. This is familiar for everyone, I believe. This is nothing but the periodic table. This is our periodic table. Everybody knows this periodic table, and everybody understands what metal, non-metal and metalloids are. So, as you can see here, with blue color metals are represented, and with yellow color non-metals are represented, and with the green color in the middle, 8 elements, only 8 elements are there which are represented in green, or you can say another shade of green. This elements, last elements, polonium and 80, symbol 80, they are actually radioactive in nature. So, they do not have a very direct application in our life, but another 6 elements, as you can see, boron, silicon, germanium, arsenic, antimony and tellurium with Te. They are usually known as metalloids. So, what is the basic most fundamental difference between metal, non-metal and metalloids, especially with respect to semiconductors? So, I believe many of you already know, but we shall discuss this. in the beginning, metals are really good conductor of electricity. Electricity. And on the other hand, non-metals are bad conductor of electricity. Non-metals cannot conduct electricity from one body to another. Let's say there is a body A, there is a body B, and you join them with, let's say, a non-metal, the electricity cannot pass through. What about metalloids? I believe most of you know they are not a very good conductor of electricity, but we cannot say that they do not conduct electricity. In other words, if I can say their conductivity of what? Conductivity of electricity can be controlled. This is the game changer for us. For metalloids, the conductivity of electricity can be controlled. We can actually control how and when to conduct electricity through a metalloid. Now, definitely a metalloid, let's say there is a rock made up of metalloid, you cannot control simply the rock thing, but the devices made up of rock. Most of you must know diode, there is a device called transistors, all right. The engineering guys, I believe they know flip flops as a device, not the footwear flip flops, all right. So, these are the devices made up of metalloids, and the electricity in electronics, in the electricity can be controlled. So, this is the genius of semiconductor, and since they can conduct electricity not in a very good manner, but at least not in a bad conductor of electricity. So, they are also called, metalloids are also called semiconductors. From here we get our word semiconductors, all right. Now, we shall move ahead. In semiconductors, we already know the genius behind semiconductors, what is the game changer behind semiconductors, the very basic thing, how and why a semiconductors works, why it works. So, there is something called impurity, something what we call as impurity. Impurity. Now, you must be knowing, and most of you, you know, from the science stream must be familiar with these words in your higher secondary schools, that impurity are induced inside a semiconductor, you can say, element. Now, the you can say the superstar, the element which actually we refer to whenever we say semiconductor, or we say you can understand the chip, the basic element that we refer to is silicon, Si, all right. And you must be knowing this from your chemistry and science classes, that silicon as an atom has 4 electrons in its outermost shell. Okay, this class will not get too technical, don't worry about that, but this is something very basic which you should know. Not maybe UPSC prelims will go in depth, but your state PSC exams can actually go and ask you questions from here, and this is something basic that you should know. So, silicon is such an element whose outermost shell has 4 electrons, and we are familiar with one element, carbon, whose outermost shell has again 4 elements, and entire organic chemistry is based upon this, all right. Now, silicon, as you can see in the diagrams above, all these plus 4 blue shells, blue circles, you can see they are silicon atoms, and how uh, perfectly they are combined with each other. In chemistry terms we call it lattice. You don't have to go there, but how perfectly their lattice is made in squares, 4 electrons. If I give you one example, just imagine this particular uh, silicon atom, okay, at the bottom, and I will just extend the same diagram once more here, and you can simply see that in the outermost shell 8 electrons are present, and somehow they are attaining the stability. All right, you must have been knowing about an octet rule. So that's how silicon is so much stable, and silicon is so perfectly aligned with other elements. Now we were talking about impurity, what this impurity was. So impurity are of two types, all right. One is positive type and one is negative type. So similarly we gave them a name, p type and n type. After this p type, we will first of all deal with p type. P type is simply positive type. Why it is positive? Because the impurity induced is of such an element where the outermost shell has 3 electrons. You can see this circle in p type, it has plus 3, it has only 3 electrons, all right. So it is lacking of 1 electron, and you can also see there is a label written hole, okay. This hole is a lacking of 1 electron. So out of all the entire lattice, every element is silicon, but at the middle of it we have induced an impurity, and that impurity is nothing but another metal or another element which has 3 electrons in its outermost shell. So what really happens, any electron can actually take its place and create a new hole, and any other electron can take its place and create a new hole, and any other electron can take its place and create a new hole, and this kind of series can go on and on. When an electricity is induced through this kind of component, through this kind of substances, electrons just move and take spaces, they try to fill up the hole, and that is how you can say electricity is conducted. You can see how the electron is moving, and in the same manner electricity is being conducted across the lattice. We will deal with this in the same manner with n type semiconductor. N type semiconductor is exactly like p type with a slight difference. The impurity in n type or negative type semiconductor, what really happens is the impurity actually has 5 electrons rather than 3. 3 electrons was actually creating a lack of electron in the outermost shell, and it was creating a hole. Instead, n type semiconductor actually creates free electron. We already know that silicon has 4, a 5 electron atom actually creates a free electron. There is a free electron. Now this free electron is very unstable. This can jump here, this can jump here, this can jump here. The free electron can actually jump across the lattice, okay, and this is how the electricity is conducted here. So this is a very basic thing. I hope you understand how a p type and n type semiconductor behaves. P type is nothing but an impurity which has a hole, which makes it a positive. We all know electron has a negative charge with it, all right. So in p type, when there is a lack of 1 electron, there is a lack of 1 negative charge. Lack of 1 negative charge is nothing but positive charge. Lack of electron is creates positive charge, and on the opposite side excess or surplus, you can say, surplus of electron is creating negative charge, because there is one extra electron, an extra negative charge. So this is creating an extra negative charge. So this surplus of electron is called n type, and this lack of electron is called p type. Don't worry about being getting into deep physics out of it, okay, but this is something very basic which you should know, which you should understand. Now moving ahead, this is the science behind it, which I believe you know already and you got to know, and we will get to know more about the semiconductor manufacturing process. As you can see in your screen, there is a very good graphic which is depicting sand. From sand we are getting silicon. This is actually called silicon ingot, INGOT, silicon ingot. And from silicon ingot we are getting a wafer, and we are from wafers we are getting an entire chip, which is actually very small in size. uh, the people who are connected, really connected with current affair, they must know, they must be knowing this already, that we are creating chips less than 2 nanometers, okay. Not we as an Indian companies, but globally there are companies which are creating chips less than 2 nanometer. India has achieved 3 nanometer success, all right, but there is a lot more work to be done. So in this uh, process, as you can see and you already understood, there is sand. You can see there is sand, and from sand we get the most basic silicon silicon compound, you must say, SiO2, silicon dioxide, all right. In your maybe geography classes you must be learning about Sial and Sima, all right. These two are the elements which are present in Earth's crust in excess. Sial we call for land surface, and Sima we call for oceanic surface, all right. So we can see silicon is present in our Earth crust in very excess amount, and the most feasible form to obtain silicon is from sand, because sand contains SiO2 uh, naturally. From sand we extract silicon, we extract silicon, and we get, you can say, a brick, a brick made up of silicon, entirely made up of silicon. This thing is known as ingot, silicon ingot. This is just a technical word which you should know, all right. And from ingot, what we do, we actually slice this ingot. Just imagine there is this brick and you are slicing it, all right. So we are getting a very thin, very small, very thin sides of very thin surface sides from the ingot. These individual surfaces are known as wafers. Wafers you already know from chocolates, that chocolates are made up of wafers, the sugary wafers. So these things are called wafers, and then there is a process, again a very technical term, but you must be knowing this. This wafer thing is actually getting etched by light, you can say a laser light, and this process is called photolithography. This wafers, imagine there is a large wafer, and laser light actually imprint a circuitry or circuit on this surface, a very thin surface, and after that this is again sliced as chip. We get individual chips from here, okay, what we call the semiconductor chip. So this is how we get a chip right from the sand. This is a very basic definition, a very basic explanation of it, but this is something which you should know, especially the technical terms like what is photolithography, okay, what is etching, what wafers actually uh, came in one of the PYQs which I was dealing with, but it was not a very direct PYQ of semiconductor topic. What ingot is, what a silicon ingot is. So these are some terms which you should be familiar with. Okay, you need not go in detail, the physics detail out of it. And yeah, with this we will be moving ahead, and we will understand what a chip really is. As you can see here, you can see there is this silicon ingot, there is a brick, there is a stone kind of thing, but entirely made up of silicon. This is the raw material. This raw material is called silicon ingot, and after that the photolithography, which I said, photolithography, the process of photolithography, it actually makes a circuit, and it takes the help of another components. These components come in form of transistors, and they entirely make this integrated circuit, which we also known as IC. IC is a word you must have heard everywhere. Okay, you may be hearing this from your electronics shop mechanic that okay, maybe IC has been burnt. वो बात भी ऐसे करेंगे कि आईसी शायद जल गई है या आईसी उड़ गई है, इस तरह से वो बात भी करेंगे. So yeah, this IC, integrated circuit thing, we get from the chip. Like the chip evolves into an IC, and this IC, lots and lots, you can understand, millions of transistor. I am saying, not saying thousands, I am saying millions. Millions of transistors actually make IC, integrated circuit. This depends upon device to device. It need not be millions of transistor in every IC, but it depends upon device to device, and many IC together makes a proper processor. Okay, the memory word you can actually deny this as of now. It makes a proper processor. You can see performs computations and stores data for devices. Okay, and this is something which I need not explain. This processor is there in every product, every appliances that you use in the childhood. You must be playing video games, even that had a processor, a very simple one, but even that had a processor. Your phone, your laptop, your cars, all of them, even the satellites, airplanes, everything, your fridge, refrigerator, if you are using some electric appliances in your kitchen, everything electric, even your trimmer, even your you can say some light stand for in your study table, even that is having a small circuitry, which you can say IC, but it all the things are containing a chip. Okay, you must be familiar with a green color board. In all the appliances there is a green color board, and there are very mesmerizing, you must say, uh, just give me 1 second. Yeah, green board, and in green board you must be looking at the circuits, and there are some devices also attached to different places. It looks like silver, but it is not actually silver. There are other alloy metals which are used for that. So I hope sorry, I hope you are very familiar with the chip design right now, how what chips actually are, how chips are made, what are the process, what process, what are the basic steps of the process, all right. And just I would take your one more time, the process of adding impurity to the silicon ingot, the process of adding impurity, silicon with impurity, this process is known as doping. This is another word which you should know. The process from which we add impurity into the silicon, you can say silicon element, silicon lattice, that is called doping. And doping again has a two form, N type or P type, which we already discussed earlier. Now moving ahead, this is the fabrication process of a chip, which we already understood. We understood what a chip really are, and these are the application. We already know the applications our entire life, especially the incoming of AI tools in our life has enhanced the importance of chips in our day to day manner. Now, there is one thing which is called GPU, graphics processing unit. You must be familiar with the term CPU right from childhood, that CPU is the brain of the computer. CPU has a evolved form, GPU. You don't have to understand it technically, but you can understand one GPU must be having at least 100 CPUs. Okay, it is a very fast, very high processing chip in reality, which can process very high amount of data, which CPU, a standalone CPU or our laptop CPU can actually not process. Okay, so GPU is a very trending term which you should know, and you can see right from smartphone to computers to our automobiles. We are getting EV automobiles, aircraft, even in satellite, sorry, power grid and medical equipment, even in defense systems. So every aspect of our life, okay, right from electric scooter to a satellite launch to again to help us, is running on GPU these days. And this explanation hardly, gives you any, gives you a better idea of why the prices of things are running up. We will be looking at it again. And this GPU thing, like I explained you earlier, semiconductor is not one industry, it is an enabler of industry. It is enabling other industries. Okay, semiconductor is one industry which is enabling other industry. The high processing GPUs are actually helping AI tools to process better, to help us better. They are actually helping smartphone smartphone industry to make a better high processing smartphones. I'm not saying this is entirely, good for the environment and everything, but that is a discussion for later classes. Similarly, we are getting high processing computers, very good quality medical equipment. So GPU as an industry, semiconductor chips as an industry is not one industry in itself, it is a proper ecosystem. It is an enabler of all the other industries. All right, and we will be moving ahead. So yeah, since I was saying it has been used in every aspect of our life, especially after the introduction of AI tools in our life. This thing, semiconductor chip, has become a topic of national security, and it is inviting players from entire geopolitics. And why it becomes, you can say, uh, more integral for our lives, because the graph, you can say, see in your screen, this graph clearly explains semiconductor manufacturing sector top 10 global ranking until FY26, financial year 26. And you can simply see Taiwan, and if you have a good understanding of the graph, Taiwan, as per data, produces more than 60% of semiconductors across the globe. South Korea, on the other hand, produces uh, around 20% semiconductor chips across the globe. So there are these two countries. There are these two countries which are actually producing, a good majority, 80% of the entire semiconductor industry, semiconductor chips of global demand. So you can see when two countries, and if you know geographically, these two are really small countries with a huge ecosystem of semiconductors, and every global power, every geopolitical power will actually have would like to advance on this sector. So this brings us that why actually we also need to progress in terms of semiconductor industry, in semiconductor ecosystem. You can see even India, it is definitely there in top 10 to 15 nations in production, but it does not cut the deal for us. Okay, we cannot stay in this position, and we need to progress, and we need to mostly become independent of other countries. If we cannot become independent, definitely not becoming dependent on other countries. Moving further, understanding the geopolitics behind semiconductor industry, this is one thing which makes us think why semiconductor manufacturing is a challenging sector. The manufacturing of semiconductor, okay, the distribution and supply thing that we can discuss later, but why manufacturing of a semiconductor is very challenging. This is a photograph that you can see. This photograph, the name of the company is actually ASML, which is hidden here. Again, due to the size of this machine, this one machine actually cost you somewhere north of 400 million US dollars. This one machine, all right, this is the cost which even the beginning of the ecosystem requires. And this machine, what we discussed in the fabrication process, this is the machine which actually performs the photolithography, which we discussed, photolithography over the wafers, which in turn further gets converted into chips. So we understood this photolithography. This is the machine which actually performs this photolithography, and this is, you can see the size of this machine, massively huge size, and this costs even the investment to begin the ecosystem, to begin the manufacturing of semiconductor is challenging at this level. We will be discussing few points here, that what are the main challenges. So main challenges you can clearly see: high capital requirement. The machine we just saw, it was of hundreds of millions of dollars, and this was just one machine, okay, for required for fabrication plants. Then there is technological complexity, okay. We again, after incredibly small scales, we also need a high level of R&D, okay, to actually reach this technology. And after that, we need highly specialized equipment. This is a very similar thing to high capital requirement. Specialized equipment in this industry will naturally demand a very high capital requirement, because you are literally working in nanometers. You are literally working in nanometers. I hope you remember the ingot thing which I told. The ingot thing is something that you can actually uh, held in your hand, okay. Now right from ingot we are going to nanometers, like we are dealing in the industry which deals in literally nanometers. So we really need highly specialized equipment, and naturally highly specialized equipment will have extremely high capital requirement. And again, point number 4 answers all of my questions. A fab, this fab is a fabrication process, cannot operate in isolation. You cannot actually depend on something, okay. You cannot have a monopoly in this sector. You cannot afford it in the future. So these are some points apart from what we discussed earlier, which actually keeps this industry on its toes, and it is also interfering with the geopolitical players. Moving forward, we will see. Okay, yeah. So you must be remembering what we discussed in the beginning of the classes, that about the Apple products price hike, a very sheer price hike, and I hope you got to know that what are the elements, what are the players involved, and uh, why it is actually getting a lot costlier, and why it is becoming a very challenging process to produce such products in future. And naturally, in your mind you must be thinking that why can't every country simply manufacture its own chips, and we got the answer for that, that we simply cannot manufacturing, even setting up an industry to manufacture these chips is a challenge in itself. This industry, you can say, is very inaccessible. Not everybody can access this industry. Even the door access requires huge sums of money, and these are the uh, sorry, these are the questions that we were discussing right from the beginning of the class. I think we have answered many of the questions here. What exactly is a semiconductor, we discussed this, and why has it become so strategically important, we right now discuss this. Why is India trying to build a semiconductor ecosystem? This is a very big question that we need to deal with, and moving ahead we will be dealing with this same question. So as you can see, India is a very, you can understand, software dominating market. Everybody knows India has IT parks in Pune, in Bangalore, in Chennai, in Hyderabad, even in Delhi NCR. So we are a very software prone market, but to jump from software to hardware is not an easy task. And here is a very brilliant, you can say, graphic depicting what are the strengths and what are the weaknesses. There is something which in weaknesses that we need to discuss more. You can say limited semiconductor fabrication ecosystem. All right, it is really very limited. Dependence on important components, equipment, materials. We actually are not producing the even if we get the raw material, we are not producing, you can say, the initial equipments which are required to build the manufacturing ecosystem. High capital requirements we have already discussed. Need for specialized talent. Okay, we need to have the that level of skilled labor and that level of R&D. Apart from skilled labor, this labor thing is skilled labor force. And infrastructure requirement, definitely we need a very grand infrastructure to even enter into this. And what India has done, so this is where we come to, this is where we come towards the our current affair part, which is India Semiconductor Mission, or ISM 2.0. So in ISM 2.0, it is uh, formally launched with the union budget. In union budget speech, the government of India has allocated 1,000 crore, 1,000 crore for ISM 2.0. All right, you can see in the key highlights, 10 ISM projects worth 1.6 lakh crore have been approved in 6 states. There is a direct PYQ right from this one point, which was asked in this year's prelims, 2026 prelims, that we will see by the end of the classes. And as you can see, moving forward, this 10 ISM projects, you can make a note and consider, you know, a good homework for you, because you must be knowing these 10 ISM projects due to the PYQ dependence. This is the vision which we need to discuss, and we know already. you know from the current affairs, ISM 1.0, it got started in 21. All right, at that time it is not written, I will be just letting you know. It was 76,000 crore. 76,000 crore was invested, and across many years now we have reached 10 projects across our country, and a big sum has been approved due to that. And we are beginning in 2026, we are beginning with ISM 2.0. We will be checking what else it has got, and these are the futuristic projections for 2029 and 2035, that we should be domestically, domestically we should be independent of at least 70 to 75% demands, and by 2035 India is looking at becoming top global semiconductor nation. And yeah, moving forward, these are the projections, and moving forward, these are the schemes under ISM. These are something which makes it a very direct questions in exams. Semiconductor fabs scheme, display fabs scheme, compound semiconductors, and ATMP OSAT scheme, all right, and DLI scheme, also known as design linked incentive scheme. We will be looking all these schemes at detail and as per the UPSC current affairs syllabus in later classes. And yeah, moving forward, I would like you to know about the other elements in current affairs, the what India has produced in ISM 1, what we discussed in ISM 1.0, whatever we discussed, we have achieved many breakthroughs as well. Out of that, the top 3 breakthroughs which I would like to discuss, one of them is Dhruv 64. Again, it has been developed by CDAC. Okay, CDAC is Premier Research Institute for Computer and Electronics in India. And then we have Dhanush. Dhanush is an indigenous SoC. What is SoC? System on chip solutions. It is more than a processor. You can understand that this one processor is equivalent to one computer in itself. All right. And then we have Dhanush Plus. It is even advanced than it is even advanced than the Dhanush variant we have. And in applications, you must may be saying that it is designed for high performance embedded systems, aerospace systems, like that. So we have developed an SoC chip, and we have an advanced version of SoC chip, and we have an indigenous chip known as Dhruv 64. This is 64-bit microprocessor which is entirely developed in India. And yeah, moving ahead, these are a couple direct PYQs from this chapter which I would like to discuss. You can see right from 2018 UPSC has their eyes on this chapter and this topic, and they are asking questions. There are some questions which are directly not linked, but you can say in the periphery of this topic there are questions right from 2016 in this topic. So we will be discussing the 2018 uh, question with reference to solar power production in India. Consider the following statements. India is the third largest in the world in manufacture of silicon wafers used in photovoltaic units. So we just discussed India is at present not even in the top 10 nations, definitely in top 15, but not in the leading nations. So we are definitely not in the we were not the third largest in the world, that too in 2018. So this statement is wrong. The solar power tariff are determined by Solar Energy Corporation of India. So this is actually wrong statement. There are I'm sorry, there are other bodies, central and state level bodies, which determine the solar power tariff. So, this is not about this is not directly from this class, but letting you know that both of these statements are wrong. So, the answer would be D here, and discussing one more PYQ which is really you can say the most recent PYQ asked in this year's exams 2026. Which of the following pair of semiconductor plants in India and their locations is not correctly matched? So, you can see there is industry name, partnership with another industry in Gujarat, Tata Semiconductor Assembly and Test Private Limited in Assam. This was the option which is actually wrong, but how will you get to determine this? You must be remembering there were 10 projects approved, which I told you that it would be a really nice note and homework for you to remember all 10 of them, because a direct question in this year UPSC prelims has been asked, and this HCL Foxconn joint was actually a wrong answer because it has been set up in Jewar. The name of the place is Jewar in UP. Jewar in UP and not in Madhya Pradesh. So, actually the right answer is C, because it is not correctly matched, and we can see 6M is established in Odisha. These 10 projects approved are being set up in 6 states. Okay. So, you can directly see 3 states, we can 4 states we can see Gujarat, Assam, UP and Odisha right in this one question. Other 2 states and what those 10 projects are, you can actually have a note of that, and it would be really brilliant to update the note later in concurrence with current affairs. And moving up to the conclusion of our classes, I really thank you for joining in, and I believe this pilot episode will pilot I have a habit of saying pilot episode. This pilot class will actually help you a lot, and we will be bringing more classes as time and situation demands. Thank you so much, guys.